Hi, welcome to StatStuff. I'm Matt Hansen. This lesson is part of an extended series on hypothesis testing in the analyze phase. In this lesson, I'll review the Chi² test that's used when comparing a proportional type of metric across two or more factors. I'll spend the first part of this lesson reviewing some of the critical concepts that can help you to understand how to use this test. But despite that, I recommend that you at least review the prior lessons on hypothesis testing if you haven't already done so. But for now, let's review again why we even need hypothesis testing.
Well, we need hypothesis testing because, remember, our goal for the project is to resolve the problem by first building a transfer function. We don't want to just alleviate the symptoms that we're seeing, but we want to get to the root cause. You may recall my example of my daughter Hannah. We don't want to just alleviate the arthritis pain that she was feeling in her leg, but we want to heal the root cause, which was the strep throat. So if we don't know what the root cause is, then that means we need to build a transfer function to figure that out. By building the transfer function, we can know what changes, that is, what improvements that we need to make that should fix that root cause. Now, if you recall, the transfer function is defined as y equals f of x. That is, the output response of y is a function of one or more input x's. It's part of the IPO flow model, again, that we described before in the IPO flow model, where we have an input that leads to a process and an output. Well, the y refers to that output. The process piece refers to the function that's applied to an x, the x being the inputs that are part of it. So it's really expressed in the IPO flow model to an equation. Now, how does this transfer function fit with hypothesis testing? Well, hypothesis testing tells us which of those x's, which of those inputs that we're looking at, are independently influencing the y, the output metric. When we reject a null hypothesis, we're building evidence proving which x's are guilty of driving the y. And what we'll do at the end is we'll compile all the evidence in the improve phase of DMAIC, and that's when we'll begin to fix those root causes or come up with a plan that's going to fix those root causes. Now that we know from the hypothesis testing which of the x's are the most critical x's that have the most influence and where we need to make the biggest changes that are going to affect our output y.
Okay, now let's review again the various steps that we follow when doing hypothesis testing.
On a high level, the steps begin with a four-step process, which was starting with a practical problem. We're stating the problem as a yes or no question, and then we want to convert that problem into a statistical problem. That's going to help us to figure out which is the right statistical tool or method we're going to use to help figure out how we're going to do the analysis. And then we apply that statistical tool or concept on it, and then we interpret the results from that and come up with some analytical answer. And then from that, we would interpret the analytical answer into some practical solution or some practical way in applying that so it makes sense to us. And at the heart of doing the hypothesis testing, again, for steps 2 or 3, that's where we drill down to 6 additional sub-processes or sub-steps in order to figure that out. So it started off with defining the objective. Then we want to state the null and the alternative hypotheses. Then we define the confidence level and the power levels based off of the alpha and beta risks that were identified. Collect the sample data, and we want to calculate the p-value. All these are part of building this statistical problem. And then once we've done that and run the test, then we interpret the results. This is going to be the point where we decide whether we're going to accept or reject a null hypothesis. This is what we'd follow when we want to go through the formal hypothesis testing.
All right, now let's review again the chart for finding the right statistical test and where the Chi² test fits into all this.
Well, in this drill down, like we've seen before, for finding the right statistical test, what we're going to be doing is working with 2 sets of data, or at least 2 or more sets of data that are all discrete values. So that means we're going to be looking at proportions types of tests, and because of that, looking at multiple factors, more than just a one-to-one comparison, but comparing at least 2 or more factors, we're going to be using a Chi² test down here.
Okay, before we dive into this test, let's review again what I mean by proportions.
Well, proportions are measurements with using discrete values, and they're generally going to be represented as a percentage. So even though they are percentages and percentages are numeric, they're not to be confused as continuous values. So just be careful. There could be some risks if you're using percentages or measures of proportion for some tests that are really designed to be used only for continuous values. So just be aware of that risk that might be there. Now, defects and defectives are the measurements we might use for measurements of proportion. So as an example here, we have 5 different units, and each of these dots represent an opportunity per unit, and the red dots represent a defect that might be within each unit. Well, based off of from a unit perspective, we might say, well, 4 of these 5 units are a defect because they have at least one of these opportunities that's a defect. So in that case, the DPMO measurement we might use is 800,000 or 80% defective. Or however, we might say from a defective perspective, that is, how defective is each unit, and if there's 9 opportunities, in this case there's 2 defects. In this next unit there's 3 defects, and so on. From a defective perspective, how defective each one is, we might say the DPU is 1.8 based off of the total number of opportunities and the number of defects we have, or it's 20% defective. Now, why are statistical tests needed for proportions? Well, simple proportions using percentages, they might be insufficient. If you're just comparing a percent to another percent, that may not be complete. You have to really account for the level of confidence that you can have in those percentages, because you may not be able to trust the raw numbers. So as an example, you might have 50% proportion of 100,000 records. Well, that's going to be very different in the implication than if you have 50% of only 100 records. So you have to account for the difference in the sample size, which could affect the overall proportion, which ultimately affects the precision of the proportion that's represented.
All right, now we can begin to define the Chi² test, which is actually categorized into 2 types of tests.
Well, first of all, when should you use a Chi² test? Well, it's used when you want to compare proportions between at least 2 or more factors or groups. Now, chi is referring to the Greek small letter x, which is again pronounced chi, and it's often referred to as the x squared, or in this case we pronounce it as chi². The test is actually comparing the actual frequency proportion of observations to an expected frequency proportion of those observations. So again, it's comparing something of the actual results compared to what would have been expected, or what should have happened if it were normal. So there are 2 types of Chi² tests that we'll be looking at. First one is the test for goodness of fit, or one variable. This is where it's comparing an observed factor with that factor's fixed or evenly proportionate set of outcomes, the set of outcomes that it would have normally expected. Again, that's why it's referring to just one variable that you're comparing. So as an example, if you have a coin, the coin has 2 types of outcomes if it's truly unbiased. Because there's 2 types of outcomes, the expected outcome should be about 50-50. One for either side. Or if you have a die that you roll, it has 6 sides on the little square die. So if it's unbiased, then we'd expect that the outcome for each side is about 1/6. Or if there are 4 candidates that are running for office, then the expected outcome for each of those candidates is about 25%. So how do you find this type of test in Minitab? You're going to go to the Stat menu, select Tables, and then select the option for Chi² goodness of fit test, or one variable. The other type of test is the test for association. It's a 2-way table, again, when you have more than just the one variable, but you have at least 2 different variables that don't have actually a fixed or evenly proportionate set of outcomes in the same way as these prior examples. So an example would be like if you're comparing the gender versus political affiliation for a group of surveyed people. Each of those groups, like for gender, you have an expected outcome like either male or female. However, when you compare them to a different group, like political affiliation, then it could be very different. So now, because you're comparing more than one variable here, the gender variable and political affiliation, you're combining the 2, the proportions are not going to be expected. So as a result, you can't run the goodness of fit test, but in this case, you'll be using the test for association. Also, like comparing the amount of training versus performance metrics for a group of employees. Again, it's not an expected outcome, so in that case you'd want to use the test for association. We'll get into examples of each of these, but to find this particular test within Minitab, you go to the Stat menu, select Tables, and you can either choose the Chi² test, the 2-way table in the worksheet, or you can select the cross-tabulation in Chi². And again, we're going to run examples through all these different types of tests here.
Now let me show you the Chi² test statistic used for calculating the Chi² goodness of fit test.
Well, the Chi² test statistics looks kind of like this. I know it looks a little bit ugly in looking at it, but let me explain a little bit what this formula means. In this example, when we're looking at the FO and FE in there, the FE refers to the frequency expected, and the FO refers to the frequency observed. Now let's go through an illustration of what this really means and how this worked for the goodness of fit type of test. Let's say we have an example where there's a coin that's tossed 100 times, and we have the results where 64 of those times it came up heads and 26 times it came up tails. So now let's compare that in here. Let's say, again, for this chart, for those that were observed in the actual results in the sample that was run, 64 of them came up as heads, 36 came up as tails. Now what we'd expect normally is to see 50 heads and 50 tails. So now in this formula that's run, the same formula that's run up here, we're taking the observed portion, which is 64, Subtract from that the expected portion, which is 50. So 64 minus 50 is 14. We're going to square that, and then we're going to divide that result by the 50, the expected portion. The result comes to 3.92. We do the same thing for the tails down here, and it comes also up to 3.92. And the total of these comes up with our Chi² test statistic. And we would use this to see what contribution each of these has to this Chi² test statistic. The p-value is what we would also look for and what's separately calculated by looking at the Chi² distribution and using that Chi² test statistic, and the degrees of freedom where we calculate it as the number of rows minus 1 times the number of columns that are used minus 1. Now Minitab fortunately is going to calculate all this for you, and so you don't have to go through all this mathematically to figure this all out. But at least this gives you some idea of how it's comparing the actual observations to what's expected, and where you can see the contribution each of these results come up to contributing toward the Chi² test statistic. But we're going to next look into a few examples of these, so hopefully it'll make even more sense looking at that.
Now let's walk through a few examples of this Chi² goodness of fit test. First, we'll start with an example of a coin toss.
In this coin toss example, what we're going to look at is we're going to say that there's a coin that was tossed 100 times and the results came up as 64 heads and 36 tails. So for the practical problem, we want to ask ourselves, is the coin unbiased with the results of 64 out of the 100 coin tosses, where 64 of those came up as heads? So for the statistical problem, we'll translate that to, first we need to figure out what's the null and alternative hypotheses that we're going to use. The null hypothesis is that the probability of heads or tails is going to be equal to 50%, which is what we'd normally expect, as the alternative hypothesis is that the probability of the heads or tails is not going to be equal to 50%. So we're going to define the confidence and power levels, and then we're going to use the default like we've used before, like 95% is our confidence level. And for the statistical problem that we're typing into Minitab, first you want to create in the worksheet a formula that looks, or values that look like this, where you have one column designated as the category, where you're defining the different values you're comparing, like in this case heads or tails, and the observation column, where you might have 64, 36. The main thing is that you have the values typed in like this. The column titles really don't matter as much. So in Minitab, you go to Stat, Tables, and then Chi² goodness of fit test in order to run this. And then we're going to select the observed counts as the observation column. And then for the other category that's included, the category column is what we're going to select over here for the column for category names. And then we're going to select equal proportions under the test, since what we're comparing here is that we're expecting the coin toss that we have is equally proportionate between the different categories. That is, since there's two categories, we're expecting equal proportions in each, which is a 50-50 chance. So we're going to select equal proportions for this. And then for the solution that we'll see from Minitab, it's going to look like this from the session window. And what we're going to look for is the p-value. In this case, the p-value is 0.005, or 0.5%. So that means there's a very small amount of risk of us being wrong if we claim a difference. In this case, we're going to reject the null hypothesis. So by rejecting the null hypothesis, we're actually accepting the alternative hypothesis, and that is the probability of heads or tails is not equal to 50% as we might have normally expected. Now, both categories of heads and tails equally contribute to the Chi² test statistic, like we've shown in the previous slide. They're both contributing to it in some way, where one is contributing proportionally to having a greater weight, and the other one is also doing an equal proportion, but it's showing up as less weight or less chance of it turning up as tails. So from a practical standpoint, what do we do with this? Well, we would answer the question as saying, no, the coin is not unbiased. That is, there does appear to be some bias. From a statistical standpoint, that's what it appears. It does appear to favor heads more than tails when you flip the coin. We can create a graph of this if we wanted to out of this type of test that's running with a Minitab that might look like this when we compare the orange expected versus the blue one reflecting the observed, where you can see just visually here there's a lot more heads that were showing up than that actually were observed than what would have been expected. So as a result, it does appear, and according to this p-value, it does appear that there is a difference or maybe some bias between when heads or tails comes up, and it seems to be favoring heads more than tails.
Now we'll walk through another example in using this test when rolling a die.
Well, for rolling a die, let's say in this example that we have a die that's rolled 120 times and it has these kind of results, where the face value, like if it turns up as a 1, was rolled 16 times. If it was rolled a 2, that came up 21 times. For when it's rolled as a 3, that came up 18 times, and so on, adding up to 120 total rolls that were observed. So for the practical problem, we want to ask ourselves, is the die unbiased based on these results that we're seeing? So we need to convert this to a statistical problem where the null and alternative hypotheses are going to be like this. The null hypothesis will be the probability of any die face is equal to 1/6, or in this case 16.7%. And the alternative hypothesis is where the probability of any die face is not equal to 1/6. It's something different than what's expected, and that's 16.7%. Then we're going to also define the confidence and power levels. We'll use the default here where the confidence level is going to be 95%. And also for the statistical problem that we type in the mini tab, we're going to use the data sheet above to type that in, and then after doing that we're going to go to the stat menu, select tables, and choose the Chi² goodness of fit test option. We're going to select observed counts and select the observation column as we have here. And then if there is a category that's included, like for this face, then we'll select face column for those category names. And then under test, we're going to select equal proportions, since the proportions for rolling a die are expected to be equal. That is, if we have the equal chance of rolling any one of these, if it's truly unbiased, then there's an equal proportion that each of these take. That's where we came up with our 1/6 or 16.7% probability. So for the statistical solution that we'll look at, we're going to come up with this kind of output that comes from Minitab. And what we're going to do is look at the p-value in here. In this case, the p-value comes up as 0.199. Since this p-value is greater than our alpha risk of 0.05, then we failed to reject the null hypothesis. That is, we failed to reject this null hypothesis that the probability of any die face is equal to 16.7%. By failing to reject it, we're saying we're actually accepting that it's innocent. We're accepting that it is actually equal to the proportions we would have expected, the equal proportions. So there is no statistical difference between these based off of this particular test. The face value of the 4, actually the face value of 4, that is, contributes the most to the Chi² test statistic. So our Chi² test statistic comes back at 7.3 in this example. But if you notice, when you compare the contribution that each of these different face values contributed toward that Chi² test statistic, the number 4 value here in this row is the largest. It has a 5 out of the 7.3, that's the largest contribution. So it appears in this case that there is, if there's anything, the 4 just stands out as being very different. In this case, we have a 4 that there was a 30 times they were observed when I would have expected each of these to be 20. The fact that I got 50% more for the 4 just makes it stand out compared to the others. But overall, there was not enough of this difference here to prove that there's an overall difference between the die face, or the probability that we would have expected. So from a practical standpoint, what do we do with this? We answer the question saying yes, the die does appear to be unbiased. And we can create a similar graph as we've had before, where we're going to compare the actual results, or the observed results, with what was expected. Now it's the orange columns that represent what's expected, and that's why they all look the same. But it's the blue columns that represent what was actually observed. And again, if we look at that 4 value on here, it really stands out. But despite it standing out, again, it's a p-value that's high enough that we failed to reject the null hypothesis. So since this number 4 face value stands out like this, what would happen if we were to multiply each of these factors, each of these observations, by 10, just simply adding a 0 to every one of these, that is, increasing the sample size? Well, then what's going to generally happen is, because there's more samples that are included, then the p-value would generally shrink, because we have more confidence and less risk to be able to prove if there's a difference. And this one that's the face value 4 will stand out more different compared to the other one. So it might look like the number 4 face value is actually biased after all. That's if we increase the number of samples. But actually, based off of the number of samples we have in this example here, it's the data that we have is insufficient to prove any bias within the die itself. So based off of what we have, we don't have enough to prove that it's biased in any way. But if we still suspect that it could be biased, we just need to collect more data and rerun the test and see if it comes out any different.
Now let's go through a more practical example of applying this test at a call center.
Well, in this call center example, we're going to look at call volume between different call centers. So for the background, we'll say that the call volume at 5 different call centers has changed over time. So we're going to have this type of chart that shows the change, and we're going to compare the differences. So across these 5 different locations for call center, their current volume is reflected here. The prior volume or the prior proportion that they had were with these percentages. So we'll type this data into our data sheet within Minitab. For the practical problem, what we want to ask ourselves is, has the volume proportion changed significantly, or at least statistically significant change, between the different call centers? So for the statistical problem, we want to state the null and alternative hypothesis, where the null hypothesis will be that the current volume proportion is actually equal to the prior volume proportion. There is no difference. The alternative is that there is some difference between the current proportions and the prior proportions. So we're going to define the confidence and power levels, and again we'll accept the default where the confidence level is 95%. And for typing it into Minitab, we're going to use the data sheet again that we have up here, and then we're going to go to Stat, Tables, Chi² Goodness of Fit Test. And then we're going to select the current volume column under the section for observed counts, and we're going to select the call center column for the section that's under category names. And then we're also going to select the prior volume for the specific proportions option. And then for the results that we get from running this test, it's going to look like this in the session window. So based off of this, we're going to look again like we had before at the p-value. In this case, the p-value comes out at 0. Since 0% chance of being wrong if we claim a difference, what that means is there's 0% risk, but we're willing to accept up to 5% risk. So since the p-value is much less than the level of risk we're willing to accept, we're going to reject the null hypothesis. By rejecting the null hypothesis, we're actually saying we're going to accept the alternative, which is there is some difference between the current volume proportion and the prior volume proportion. So in here, what we're also going to further look into is that Chicago and St. Louis seem to contribute the most to the Chi² statistic. So what does that mean? Well, again, if we look at these values in here, the total Chi² test statistic comes back as 901. So we look for each of these different categories, which one is making the biggest contribution. Well, Chicago has the largest contribution to the 901. About 2/3 of that is represented by Chicago. And there's another large portion represented by St. Louis. So whatever change occurred, most of it seemed to occur within Chicago, and the next largest change seemed to occur within St. Louis. And because of these huge contributions that they're making, it's probably what's driving a lot of this p-value to be down. It's giving us, again, greater confidence that there is something different that occurred between the current volume and the prior volume proportions. So from a practical standpoint, we would answer the question saying, yes, the volume proportion has changed between the call centers over these different time periods. Again, we're going to be looking at a chart that can be output from this, where we compare the orange columns. In this case, it's not equal like we've seen before for the expected counts, but we define the expected counts based off of what the prior volume was. And that's what's reflected here in what's orange. And the blue represents what we actually observed for the current volume. So based off of this, here's again the largest difference that we're seeing between Chicago and Phoenix. Now, according to this, it doesn't look like it's very huge, but you'll notice Miami looks very similar. Reno looks very similar. But most of the difference that we're seeing is this gap for Chicago and the gap for St. Louis, where they have the largest difference between them. There also seems to be a similar gap for Phoenix, but because the volume is so high, it seems to be showing that it didn't make that big of a difference. But since Chicago is much less in volume, and the gap between the expected and observed is also much greater than the gap for St. Louis, this is probably why Chicago stands out as making the biggest contribution toward this difference that we're observing between the current and prior volume proportions.
Now let's explore the other type of Chi² test, which is for associations.
All right, now we're going to be looking at the Chi² test statistic that is for associations, which is a little bit different than the goodness of fit test that we just looked at. So how does this Chi² test statistic work for associations? Well, let's use an example of as if we surveyed 1,000 men and women and we surveyed them about their political affiliation. So here might be the results we might have seen based off of this matrix. So we have the columns representing here the 3 basic affiliations, where it's liberal, moderate, or conservative, represented here in these different columns. And then we have the men, the gender between the two of them, that is the men and women. So all together as a matrix, we'd see this cell represents the liberal men, and then here's the moderate men and the conservative men, and then likewise under this column and this row, we see this would represent the liberal women, moderate women, or conservative women. Well, for those that were surveyed from the results, it might look like this kind of proportion, which is just, again, a general example. This is not based off of real data. So we might say that there's 512 men that were surveyed, 488 women that were surveyed, for a total of 1,000 who were surveyed. Among those who were surveyed, 275 were liberal, 416 were moderate, and 309 were conservative. So based off of that, we would build a Chi² test statistic to help calculate the expected counts that we have based off of these 6-factor combinations in these cells in the matrix. So the way to do that is, we'd see that in example, 51.2% of those surveyed are men. That's based off of this number here. If there are 1,000 surveyed, 512 were men. Well, that means 51.2% of those who were surveyed were men. And we'd also see that 27.5% of those who were surveyed were liberal. Well, therefore, if we just multiply the two of them, 51.2% times 27.5%, that comes up to 14.1%. So with 14.1% of the 1,000, that's the number we plug into this cell of the expected number of liberal men that we'd expect to see. And we do that same kind of calculation for each of these cells, again, all equaling up to 1,000. So this is just telling us of all the men that we surveyed and those who were, in this example, liberal, here's the number that we'd expect to see for liberal men. Likewise, number of men we'd see, the total number who are moderate, here's the expected portion we'd expect to see of moderate men, and so on for each of these different cells. So what we do next is we would look at the actual observations, and here's where we would see maybe the actual results if we were to run a test. Again, this is all fictitious data, but based off of this, we compare our actual results with what was expected in order to assess the differences between the two of them.
Let's see how this particular test looks when we run through it that example of the political affiliations.
Alright, so now as we look into this example for comparing the gender versus political affiliation, what we're going to say is the background is that there was 1,000 men and women that were surveyed about their political affiliation, and we want to know, is there a statistical difference in the political affiliation between men and women, at least among those who were surveyed? So for a statistical problem, we're going to again state the null and alternative hypotheses, where the null hypothesis is that the proportions of political affiliation for men are equal to the proportions of political affiliation for women, or at least compared to what we've observed and what would be expected. The alternative is that there is a difference between them. They're not equal to each other. That's our alternative hypothesis. For the confidence and power levels, we'll use the default again of 95% for a confidence level. And for typing this in the Minitab, again, we're going to work with the data sheet that was shown on the prior slide that we're going to type into Minitab itself. And in Minitab, we're going to go to Stat Tables, Chi² Test 2A Table in Worksheet, and use this method when we're actually going to work with the data that was as a summary in the worksheet. And then in the section that says columns containing the table box, we're going to select the liberal, moderate, and conservative columns as are laid out in there. Now for the results that we're going to look at, the session window results are going to look something like this. When interpreting those results, we're first going to be looking for the p-value. In this case, the p-value shows up as 0. And because this p-value is less than the amount of risk that we're willing to accept, now we can say we're going to reject the null hypothesis. That is, we're rejecting this null hypothesis here, and we're going to accept the alternative, which would allow us to conclude that there is some sort of difference, proportional difference, between the political affiliation for men and the political affiliation for women. And so we might ask ourselves next, which group contributed the most to the Chi² test statistic? Well, according to this, the Chi² test statistic is 15.879, or almost 16. So in this case, what we're going to look at is the breakout that it has for each of these portions that are listed in here. So what we have, the way that's read is the first value that's within here, like under liberal, and 1 representing like the men, that's the actual that we've seen, 125. The number beneath that represents the expected, 140.8, or averaging it to 141. The number beneath that represents the Chi² test statistic, or the contribution it has to the Chi² test statistic. So what we're looking at when we want to compare this type of group here for the liberal men, moderate men and conservative men, and so on for the women as well. What we want to look for is who's got the greatest contribution. So if it's 16 is our highest number, then who has the highest contribution? Well, according to this, it looks like moderate, and this represents the women in this row. The moderate women have the largest contribution of 4.7, and it's not that far behind between the 4.5 represented here for the men, the moderate men. So as a practical problem, we might answer it as saying, yes, there is a statistical difference in the political affiliations between men and women. So from a practical stance, how do we interpret it? Well, we'd say most of the difference that we're seeing is driven by those who are moderate men and moderate women, where we have more moderate men that were observed than what we would normally expect, and fewer moderate women observed than what we would have normally expected. So we turn our focus to focusing on the moderate men and moderate women, since those had the highest contribution to the Chi² test statistic. So we'd say yes, there is a difference because our p-value tells us that, but we would turn our focus more specifically to the moderate men and women because they contributed most to this Chi² test statistic.
Now let's try a more practical example when we run the test when comparing different employees or clerks.
In this example, we're going to be comparing clerk values versus category A based off of the sample data file that we have available. Category A would represent some color. So they're basically arbitrary values, and they're arbitrary values represented in the clerk column and the category A column that's supplied in the mini-tab sample data file that's included in this website. So the practical problem we might ask ourselves is there a statistical difference between clerks and the colors that we've noted in category A? Well, the statistical problem for this would be, again, starting off with defining the null and alternative hypotheses, where we'd say the null hypothesis is the proportion of each clerk in color is equal to the proportion of each other clerk in color, where the alternative hypothesis is the proportion of each clerk in color is not equal to the proportion of each other clerk in color. For the confidence and power levels, we're going to use the default of 95% for a confidence level. And for how we type this into Minitab, it's going to look like this. We're going to use the example of the cross-tabulation in Chi² that's under the Stat and Tables menus from within Minitab. And this is when we have a lot of detailed data that we're going to be looking at, when this one might be an advantageous form of the Chi² test to run. So in the 4 rows field that's selected in there, we're going to select clerk. And then for the 4 columns field, we're going to select category A. And then in the display section, we're going to select category. We're going to select the counts box under here. That's what we want to see in the counts. And then we select the Chi² button, and it opens up a new dialog box. And normally, what I like to see when I select that option is I like to check these boxes here: the Chi² analysis, the expected cell counts, as well as each cell's contribution to the Chi² statistic. So what does this cross-tabulation actually do? Well, it's taking the detailed data in the worksheet and it's building a cross-tabulated table, which is like a pivot table that's typically used within Excel. And it performs the same type of Chi² analysis that we've seen before, where it's comparing the expected versus the actual observations. But when it lays it out, allowing for more detail when you have a lot more items that you're comparing between, in this example, like the multiple items for clerk as well as multiple items for category A, or the color that's represented. So we'll see in the results here, what we look at it is the solution is going to look something like this. The output that comes from the session window from within Minitab is going to look something like this when we run it. So we would interpret it the same exact way as we had before for the other test. We look for the p-value, and it gives us 2 different types of tests: the Pearson Chi² as well as the likelihood ratio Chi². But for both of them, what I usually like to refer to is this last one, the likelihood ratio Chi², but you might refer to the other one, the Pearson one, if you have a different reason or preference for that. But even so, for being more conservative, I like to use the likelihood ratio. And in this case, the p-value comes out as 0.058. That is 5.8%. Again, since that p-value is greater than the 5% risk we're willing to accept, then we fail to reject a null hypothesis. That means we accept that null hypothesis, that there is no difference between them. They all are operating at about the same. So from a practical standpoint, we would say that we would answer the question, no, there is no statistical difference in the proportions between clerks and colors. However, how would you practically interpret the results for the p-value and the Chi² test statistic? Well, in this case, what I would say is the p-value, I'm looking for something less than 5% in order to have the proof beyond a reasonable doubt that there is some difference between at least one or more of these different matrices or these cells that are within the matrix that would say it's different, statistically different than the others. So because it's greater than my alpha risk, it's also now it's less than my beta risk. I'm willing to accept 10% for beta risk. So that means I have a lot of data. I have a lot of evidence to prove that there might be some difference here, but not enough to conclusively prove beyond my reasonable doubt threshold, which is the 5% risk, to that conclusively say that there is a difference between them. So because I'm within that alpha and beta risk range between 5 and 10% that I've predefined, then there might be something going on. And because of that, I might want to explore a little bit further. So I might look at here, what is my Chi² test statistic, which is 30.78 or almost 31, and I look at the contribution that each one of these values had made to that Chi² test statistic. Well, the contribution is represented as the third value in each one of these. So when it says here down at the bottom, it defines the cell contents. The first number represents the count. So in this one for Sally here, aligned with blue, 3, where was the count, the actual observations. The one number beneath that is the expected count. So I expected there to be about 2, or 1.96 as the result. The contribution it has to the Chi², in this case for Sally, it's 0.55. That's relatively small compared to the overall Chi² test statistic. So which one of these has the highest contribution to the Chi² test statistic? Well, it looks like Peter does. Peter has some high ones in here, but it also looks like Mary does. So we look at this third number within each of these cells, and according to this, it looks like Mary with green is the highest number, which is a 5.5 or almost 6. Next to that would probably be this one, Peter and White, having this larger contribution. So because I fall within this range of the 5 and 10% of my alpha and beta risk, I might say I need to go back and get some more data. And if I get more data, more samples, it will help either increase my level of risk, and by increasing my level of risk beyond the beta risk, then I can conclusively say, yes, there is no difference between each of these values that I'm comparing. They all seem to be about the same. Or having more data might be able to reduce my risk or reduce my p-value, and by doing that, I'd be able to conclude that there is some difference between them. And if there is a difference, the difference is probably going to end up being with Mary aligned with green here, or also maybe Peter aligned with white, simply because they're making the largest contribution to that Chi² test statistic.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
I'd like you to refer back to the critical metric and those at least 5 different factors you've hopefully identified before we even started looking into all this hypothesis testing, and select at least 3 factors that are discrete values. You might have to refer some additional values if you haven't already included those among your 5 factors. So any other factors you might have in your organization you might be able to use for this exercise as well. Before you run the Chi² test though, ask yourself, does any combination of the factors appear to be imbalanced just based off of the surface without running the statistical test? After you run the Chi² test, now you might ask yourself what combination of factors are statistically different, if any of them. If the answers you have to those 2 prior questions are different, then how does that difference affect how you typically measure and communicate that within your organization? For example, does the difference affect any financial decisions that are made, such as how people are compensated, or any process changes that might be made, that is, how the process may need to be modified, or any other types of critical actions? If it does make a difference, then how should the results from this Chi² test be used to influence your organization? Should they change how the factors are compared? That is, if you're comparing them across different times, locations, or groups, should it change how you compare them? Or should they change how the factors are being measured currently? Or should it change how we react when we compare the factors within this way?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.